Just brought a little picture along, the effect of induced flow and angle of attack. There's the normal story. We've got the induced flow, the tip vortices, and they are flying around it. No problem. All right, the induced flow, and that is that part. Okay, you can see because the induced flow, now remember that is the flow that's going down. That's the flow that's going down. Because of that, the blade angle is that whole angle, but the angle of attack is reduced. Now, the rotor blades do not stall because of the blade angle. It stalls because of the angle of attack. And the average angle of attack for a blade to stall is around about 16 degrees. All right. So now you can look and you can see on the same picture, if we look at the root blades here, they're going faster. The blade angle might be higher. This is the root, sorry, this was the tip, eh? So the inside of the blade here, the root side, you can see the angle is already higher, and that is obviously because of washout and design and so on. I'm not going to go into that now. But the net effect stays the same. Now when the rate of descent increases, the induced air flow, remember we're talking at the tip again, this is how it looks. The moment if you increase it, then you will see actually that the net effect of the downwash is less. And because the downwash is less, this angle has actually in fact increased. Now remember, that is the angle that if it's sufficiently increased. But remember, that's at the tip, so let's have a look at the root. The blade root, this is the one from the previous drawing, and here now the induced flow, look, it's exactly the same picture that I've taken. The blade angle stays exactly the same in both these cases. There's no difference. But because the induced flow is reduced, the effective angle of attack has increased. The effective angle, the resultant angle of attack, the blade will stall because of the resultant angle of attack. Now if this is the beginning and you increase the rate further, then this induced flow through the blades that come down will be becoming less and less. The net effect will become less and less and less and less because of the opposing airflow. And therefore, the net effect will be that the angle of attack actually increases all the time. All that you now need to do is put more power. How do you put power? You're going to pull collective. What happens when you pull collective? You're increasing the angle of attack. Voila. There you go. Sorry. Voila, I didn't mean that on you. Maximum angle of attack per blade angle. As rate of the increase, angle of stall increases, and as I said there, the stalling of the blade now spreads to the tip. We're talking about the opposing. There you can see that the two are now exactly the same. Therefore, the blade angle and the angle of attack now becomes one. Now, quick. We've got to look at this one nicely here. If we talk about lowering the collective breach, now you increase the rate of D. If the increase of rate of D, then the angle of attack reduces due to the reasons I've just given. If you increase the collective pitch, you increase the angle of attack. If you increase the angle of the collective pitch, you worsen the stall and the entire blade. Now we're in a catch-22. Damned if we do, damned if we don't. Any of the two. Where you are, when you have reached the condition with where the collective power flight is sitting at that moment. Remember, all the effects has now come into play for that specific setting on the collective. So if you pull, you're worsening the case. If you dump, you're worsening the case. Obviously for the new effect, it will settle again, and then from there you will have the same. So once this stalling effect is set up and the opposing flows have come to a point, it's not going to work for you anymore. So Yeah, but Charlie, you remember I was sitting in a rate of descent and I pulled a lot of power and the helicopter stopped. Yeah, of course, you can. Because you weren't in a stalled situation. Yeah, but no, wait now. The thing is, are you going to sit at 100 or 200 feet above the ground and figure out what the hell is wrong? Remember, if you lost your rotor RPM, you're already sitting with a high rate of descent that gets there. The rotor RPM in a hover was already there because you didn't have enough power available for the condition that you are in. Pulling any more collective pitch will worsen that. Dumping will worsen it as well. But remember, the natural thing is, oh, I've got to power, I've got to dump. Okay, we'll get to that one and we'll see what the sort of net effect of that is. But here you can see, and that is quite clear, that the remedy for this state, once you're into vortex ring state, is not to go along with the collective pitch. Now I'm burning a couple of toes. All right, but let's carry on from there. So you are trapped in a vortex ring state. There you've got all your indicious flows, there's the opposing flows, and everything is doing that, and you are sort of trapped inside here. Once you are trapped inside, the CP, collective pitch, is no-go. Because whatever you're going to do is just going to increase or worsen this effect. All right, so what must we do? Here you're sitting in affected air, and I'm just trying to, give it in a more graphic way. In other words, we say that underneath the helicopter, this area here, and obviously that's because we are descending into, that is the affected air, you're descending. The big thing about it is you must get out of that. How do you get out of it? Well, you fly out of it. And what if I'm too close to the ground? Well, then you're not going to fly out of it. But we'll get to that. So the nose must go forward because you must go from the affected to the unaffected stage. You've got to get there. What has that got to do with the collective pitch? Well, nothing. Yeah, but Charlie, it doesn't make sense because, the rotor RPM drooped because I had too much collective. No, it wasn't because you had too much collective, you had too little power. But then it's hand in hand. Doesn't really matter, does it? The main rotor RPM has now drooped. You haven't got main rotor RPM to sustain your flight. And as you pull power, the main rotor RPM will just get less and less and less. Therefore, you want to go down. Your problem is now you've got no speed, you dump and you descend faster. And I talk, I grew up that you would talk, we would say things like, for instance, it's the last straw that breaks the camel's back. All right. So here's the camel. Here I'm loading the back. And I'm loading it, I'm still okay. There the revs comes down. It's that last little bit, it's the last straw that is breaking the camel's back. Now we can't sustain it. What must I remove? Not the hell damn pack, you just remove the straw. So it is very natural to want to go down on the collective. But I promise you that is not an answer, because taking away the collective, you're setting up a rate of D. You're increasing it. That means there's a higher energy. There's an acceleration that you've got to overcome. Of course, if you're sitting at 3,000 feet above the ground, who cares? You can put you in a fully probably developed vortex ring state, and you might be able to fly yourself out if you've got enough height. But guys, we don't work at those heights. We don't necessarily hover at those heights. Heights that we hover at, the practical application of a helicopter is anything up to 400 and 500 feet, and above that, not really. I'm talking about low air speeds. So your game guy is working at 100 and 120 foot above the ground, where he's now watching for the game and what is going to happen. He all of a sudden runs out of the stuff. Now he dumps. Oh, it would have taken, let's say, 10 seconds to impact. Now it's going to take 8 seconds to impact. Really? Really? The collective pitch is not the answer. Now, if you're teaching stuff out there, remember from a practical application, yes, we want to take about that little bit away. You can take that little bit away, but if you take anything really a lot away, if it makes you feel better, take that little bit away. But to take away a lot just increases your rate of DEF, and that puts you in a different complexity. So, vortex ring state, effect of the vortex ring state, significant vibration caused by vortices forming on the breaking away at the root, random pitching, rolling due to the complex airflow causing the rotor blades to flap without a control inputs. These are all aerodynamic stuff that I'm giving you. Fluctuating powder bond, because of all this, that's there. I've never been in the situation where I needed the you know, or I noticed even the fluctuating power demand. That's a very, very far advanced stage. I don't think you know, most of the guys that sits in the hover, they think they're there, they dump, they go fast to the ground, they try and go faster, then there's no more height to recover. And remember, the height that you got is potential energy. And the only thing that can save your bacon here is kinetic energy. Now, the kinetic energy is your forward speed. That depends on the amount of height that you have. If you have no height, there's nothing to transfer. If the engine has got no more power to give it to you, then what else is there? So by dumping, you're just throwing the potential energy out of the window. How clever is that? Oh, Charlie, no, but there's some other serious maneuvers, you know. The guys say if you sit there and you vortex ring, you torque it and you bank it and you bunt it. And guys, this thingy at the back here, called a tail rotor, maybe it takes up 8% of the power. But in stress conditions like this, and when you're hard maneuvering and low, this can take up to 15% of your engine power away. You've already got not enough power. Why would you increase or decrease actually the power available for the main rotor blades? Because that's your problem. You see, we do stuff like that because we don't understand. So yawing is not the answer, because you're throwing away energy that you haven't got anyway. Yeah, but the guy said to me, you know, the quickest way to get out is do this wild banking maneuver and you're out of it. Of course it's the quickest way. To fly it out like that is a little bit slower than falling out of it like that. I agree. All right, so what are you telling me? All that I'm telling you, once you're out of it, is it easier to recover when you're now 10 foot or 20 foot from the ground like this, or like this? Which one would you prefer? And if it didn't work, what's going to save your bacon? Guys, let's just be realistic. When we apply these things, if you're sitting 1,000 and 2,000 and 3,000 feet by the ground, you can probably do anything with this and try and tell the guys, oh, this is how we recover and it's easy. This is not where we apply the helicopter. If you apply that nonsense close to the ground, you're gonna. So yeah, there's weird and wonderful things we can do. And the guys are doing aerobatics with helicopters, and they're doing this, and they're getting into all fancy stuff. Yes. Have you seen any of those movies about this, that the guys are doing it at low level? No. They don't. When you get into these situations, you need height to be able to recover from a trouble. The thing is, with a game pilot and with your normal operation on ships and at sea and with boats and wherever we use this as a practical application tool, and then we also chase jackals and stuff like that, and everybody tries and do that. They don't really know what they're doing, they don't understand the aerodynamics, and they really put themselves immediately into harm's way. Oh, it's not that they cannot fly. That's, guys, the accident rate primary reason is loss of control. not loss of mind. Okay, all right. So random yawing, slow control responses, and so on. A rapid decrease and a high rate of descent. Now, when are you going to see that there's this significantly high rate of descent? Well, 50 foot above the ground? Is there time to wait for this? I don't think so. So remember, it's one thing to look at the aerodynamics, it's another thing to put ourselves in the practical environment. So how do we apply this? Good. In the vortex string stage, allowed to develop very high rate of descent. Its incipient stages can be identified, company, blah, blah, blah. Because of recoveries from a fully developed vortex string state may be impossible because control is restricted. Now, the recovery requires the following, and I need you to look here. Increasing the airspeed by a large nose down attitude change. So yeah, you can now say to me, yeah, this is quicker this way than that way. It's got the same net effect on the sentence. But the sentence was not written for people that's in trouble 100 feet above the ground, necessarily. That's why I don't like this hard maneuvering to the sides. Forward. If you are sitting with a very strong wind from the side, yeah, of course, you can go into wind. But, you know, I don't want aerodynamically to make this thing not working. Look at it. They say if you have sufficient height away, you can enter auto rotation. All right, what is sufficient height for auto rotation? Come on. You shouldn't enter a fully fledged auto rotation below 800 feet. This is not a thing that you can say, okay, here I'm sitting at 100 and 120 feet, I think I'm going to auto-rotate. There's no way. The moment you go down the collective, you get yourself into the ground. So this is only when there is sufficient height. And you really, really, really got to make sure that that is the condition. Well, I know where I'm working. I know that I'm working in at low level and I can't work with this. I really do know that. And that is why I make sure that I use the right techniques. And this is not the technique that you use when you're at low level. You can't. Because you're low level and you do that, you will not have enough time to enter an auto rotation and to flare and stop the auto rotation and stop the rate of descent before you get to the ground. So there's many arguments out there, and the arguments holds all true if you've got the height from the moon to the ground. Helicopter guys don't operate that high. You know, anything above like 1,000 feet above the ground is nosebleed height. We don't like to be in that environment. But no one that actually physically applies the helicopter in its unique capabilities, in other words, slow speed hovering mode and nobody flies that at 3,000 and 4,000 feet. So let's just get real about this one. Avoidance, vertical descent. Now please, this is where everybody must pay serious attention, because look, it's all fine. Let's do the aerodynamics and let's test your aerodynamic knowledge. But now we must apply the aerodynamic knowledge, because the knowledge without recognizing an application of the knowledge in the real state is going to make that you're not going to necessarily walk away. We must walk away. So listen. So I say, when descending vertically into a confined area, okay, above the level of sickles, blah, 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 the rule is that below 20 knots. Now, you can make your rule whatever you like. 40 knots is this really sort of magic helicopter number. So when you get to 40 knots, I've just got to be a little bit more aerodynamically correct, and that's why I say it there. Me, say to the guys, man, the only speeds that you need to know is 40 knots, auto rotation speed, rest optional. Because when you cruise is what you get. Okay, all right. Aim for 300 feet a minute. You don't want more than 300 feet a minute. Let me just change that quickly there. If it's not able to maintain it, then you must if you are not able to contain 500 feet a minute, what then? If you cannot contain the 300 feet a minute, go to 500 and you try, you can't contain it. Then you can't contain it. Then the chances of it increasing. But when it gets to 800 feet, after that you're in trouble. So we need sort of like a buffer. There should be an area between we're okay, we're not okay. We could be okay or not okay. So between, we say 300 feet is what we're aiming for. You get up to 500 feet, you'll probably be okay. But if you find that coming up to 500, you're testing, and you see, whoa, I can't arrest the rate of descent. I can't control it to a lesser rate. Break off. Break off. How do you break off? Well, this is what we've just done. Just push the nose forward. Fly out of it. Fly out of it. You need speed. You need speed. You don't need this vertical speed because that is what stalled your disc. So you need to get out of that. All right? Don't put yourself in a huge, unusual attitude after that. Remember, once you're outside the bad air, you still got to recover with how it left to you at that moment in time. And then, yeah, past 800 feet, you're scratching on the lion's thingies there. Okay, steep approach. Large and mischarged steep approach causing condition for which in control rate of D, again 300 feet. The story now actually starts repeating itself, and it actually makes it quite easy. Downwind maneuvers, right and low, negative airspeed. Note that the indicated airspeed and not the ground speed is important, guys. Please remember that. Everything and the control, and when we look at the other upset recoveries that I'm working on, it goes about the stability of the aircraft depends on airspeed or indicated airspeed. It's what we as pilots can see. That is what we're referring to here, not ground speed. Ground speed has got only the consequence of the relativity between your speed and the ground when you reach it. But before we get there, the ground speed has got no effect on the stability, neither the pitching stability, longitudinal stability, nothing. All right? So we'll get to that thing. Quick stop flares when helicopters flared in a quick stop. Woo! Go and look at the presentation on the quick stop maneuvers. You want to get yourself in trouble, this is where you get yourself in trouble. It's got to be end to end. There's got to be a maximum nose. There's got to be a time when you have to start increasing the collective. And you will not set up a rate of descent in any of these cases. You know, we respond subconsciously to the things that were enforced in us. If it's never been enforced, if we've been doing the wrong thing all the time, then that will be your first instinctive maneuver, and your instinctive wrong maneuver can put you into trouble straight away. That's why to take people from basic flying to advanced flying takes basic aerodynamics applied into the advanced. Then you teach that. You cannot say to a guy, don't do that, do it and see that it's going. A lot of things I show the guys at extra height, and then I show them what is the height loss, and they say, damn, if I did that at low level, I was a goner. Well, I'm so sorry a lot of people didn't know that, because, you know, that's like self-induced. Confusion, too little power to sustain out of ground hover can result in an excess rate of D, start of the vortex ring spinning on the low power. And this is where we're sitting. We're sitting in the out of ground effect. We've got too little speed. We're sitting around there. All of a sudden we're running out of power, and what now? Now immediately, whoa, we're in a fully fledged vortex ring state. Yes, you are on your way to a vortex ring state due to the fact that you could not sustain, and that was not a pilot-induced rate of descent. It was an engine, or the engine didn't stop the rate of descent. Okay, it doesn't matter how the rate of descent started. It started. So whether you induced it or the droop in the main rotor RPM, it really doesn't matter. It's going down. All right, so the vibration associated with transitional flight, this is a story. I mean, remember transitional, you know, a lot of times we do mountain flying and stuff like that, and you really sit in that area and you start flying at low speed, the helicopter will vibrate crazily. Are you not in trouble? You're not. Your rate of descent is good. You've still got power. You are just sitting in a region where that is. If you sit in the hover and you start losing main rotor RPM and the aircraft sounds, there's going to be. But it doesn't mean that you're in a fully fledged. But even if you believe in the fully fledged, if you dump, low level, if you walk away, you're lucky. It's normal not to walk away. Push nose forward and fly out of the bad air. Vibration due to poor wind condition, turbulent air, I spoke about that. Common errors, reduce power in a tight circuit. Go and look at the presentation on tight circuits. That you can get away from this ill-advised way that people are doing. Game pilots are taught wrong. Air Force pilots are taught wrong. People are taught wrong. So please have a look. But reduce power in the turn here, especially for you guys flying turbines. It's a killer. It's a long lecture. I'm not going to go into that now. But the correct way to do tight circuits, we'll get to that. Allow the rate of descent to develop during a quick stop. We've spoken about that. Approach and flare downwind, we talked about. Dump to recover power and out of grounded tank when the main rotor RPM decays. Dumping is the problem when power is infinite and marginal. Yaw to increase disk efficiency. Listen to this. Wait, let me get a red pen there. Tail application takes the energy away from the available power. The pool of power is deteriorated by excessive use of tail rotor. Yeah, but Charlie, you don't understand. If I yaw this thing, you know, then I get more effective. Your blades are stalled. When the blades are stalled, it doesn't matter whether you're turning. It will make it just more stalled or less stalled, but it's not going to unstall it. The net effect is not big enough. That is not your problem. Your problem is to get out of the dead air. Sorry, I know I'm a little bit pertinent, but I got to get this thing down. Transitional vertical rate of descent in excess of 300 feet. Now we know that, and if you ignore the wind, you're an idiot for starters. The bottom line of vortex state recovery is the following. Do not apply power, as this will aggravate the state. Yeah, but Johnny, there's a little bit of power and a little bit of that. We found that the little bit of all right. Okay. In ideal circumstances, I can find many things. I'm showing you aerodynamically that it really doesn't matter. If it makes you feel better to take a little bit, to remember, but I said don't take away the whole pack on the camel's back. Just take away the last straw. If you take away the pack, you're going to increase your rate of descent. That's going to crowd my power. You haven't got the height, you haven't got the potential energy, you haven't got the kinetic energy to start with, and the inevitable is going to be the inevitable. You have to get this one. Do not make another maneuver other than flying out. But if you avoid, obviously, to avoid an obstacle. Okay, so if I push forward, here's a tree. Of course, I'm going to get out of the way, guys. I mean, come on. Be realistic. Yeah, I'm talking about what is really required and so on. Must change potential energy. Look at this. We must change potential energy into kinetic energy. Height into speed. Guys and girls, height into speed. If you've got no height, you cannot change it into speed. If you've got height and you change it into vertical speed, it doesn't help a bit. It's not going to do nothing. You're trapped. You must get out of the trap. Must fly out of the recirculating air. There I said that. This is very, very, I'd like, well, I'm not going to change the color of the highlighter. That should have been another color. Forward is the best option to clear the obstacle. Any other maneuver, obviously, to avoid the obstacle. Settling with power is an angle of attack and as such a stall problem with only airspeed that can solve it. That is the crux of why I'm doing this lecture. Every accident report I do and I get stuff like that, I feel so sorry because it's not a bad pilot. It was just a bad teacher. They didn't teach him. They didn't teach him aerodynamics. They didn't application. Hey guys, I fly fixed wings as well. Fixed wings is difficult to see if the aerodynamics is really the thing. You know, it's not like that in your face. In a helicopter, the aerodynamics is right in your face. If you know that in aerodynamics, it gives you just 100% better chance. All right, but remember, everything needs to start with the correct training. So, quick reaction when operating close to the ground is obviously imperative. Avoiding the vortex ring state, always ensure enough power for the out of ground effect hover. Don't get caught out now. Always make wind, or you must take wind into consideration. Always end a hard maneuver into wind. In steep and tight square, do not reduce power during the onset of an actual turn. When we teach people to do steep turns, we don't tell them to do a steep turn with decreasing power, not in a fixed wing, not in a helicopter. Why are you doing it in a helicopter? Oh no, I'm doing a tight circuit. A tight circuit is steep, it's just a steeper turn. Anyway, we'll get to that one. In turbine helicopters, always feed the power in. There's that 40 knot thing. Guys, at 40 knots, you've got to warn the engines in a turbine. Don't know how clever you think you are. I don't know what fancy helicopter you think. And then just remember what we are used to. So today I'm flying a Super Puma, tomorrow I'm flying an Alouette, and the day after this I'm flying a R22. R22 is a piston. It doesn't suffer from the same problems as, for instance, a Super Puma, which does not suffer the same symptoms as an Alouette or Squirrel for that matter. So teach generic correctness, because I go from aircraft type to aircraft, I must always have the right one there. Yeah, but I'm only going to fly Robinsons for the rest of my life. Okay. I don't think so. Alright, during a quick stop, feed the power in early. Always avoid setting up a rate of descent. We've talked about that when running out of power, do not reduce power as to set up a rate of descent. That will need extra power. Now it comes on to the same things, blah, blah, don't do that. Okay, that was the wrong knob, and there, get airspeed. That is the primary. Conclusion of vortex ring state. Now, I get my referencings from the AP3456A. That's what the Royal Air Force uses, and that's what a lot of people uses. That is probably the best reference that I can give you. There's a lot of other stuff that's right. Be very careful of reading articles of somebody that discovered something. Yeah, well, it was this well-known guy. He's got a great name, guys. Does he know what he's talking about at low level? Is he a test pilot, or is he a pilot that is doing the work at crude level? Oops, sorry test pilots, didn't want to do that one. Any method taught? Alright, wait, I've got to get the right color here. Any other method taught is void of aerodynamic truths. Now, you've got complaints and stuff, send it to me and we will sort it out aerodynamically. And if you are right, man, I'll be the first one to say, okay guys, you can also use this method, this is how we're going to do it, and this is how we're going to do that. But until then, be very careful of articles that's giving you, you know, it's not well researched. Use the well researched stuff. Remember, and I'm going to make it large now. Okay, I just think these things out, but this jumps out at me and said, fly it out, do not dump it out. Hello? Fly it out, do not dump it out. Fly it out, do not dump it out. That's all I can say. That is the end of the vortex ring state. So what? Are you going to end up in a vortex ring state every day? Of course not. Do you need to know the aerodynamics? Yes. Do you need to know the symptoms? Yes. Should you have been shown how to do stuff like this? Yes. Will people show you how to get into a fully fledged vortex ring state? No. Will you always practice at height? Yes. What will you practice? The correct methods. Until next time.